Let's take a look at the problems on page 366, and one of the primary foci of this particular set of problems is to think about the inverse trig integration. And I put a little reminder up in the right hand corner. Hopefully those formulas are starting to stick into your brain. So we will be using those, but this set does not just include inverse trig integrals. It also includes some other things. So we have to analyze each situation to figure out the best way to move forward. So let's go ahead and jump in. Problem number 1. The first thing I notice is I can bring that 5 coefficient out front, and because of the square root, I'm thinking that we're likely headed to inverse sign. So I have 1 over the square root of 9 minus x squared. And remember that that's a dx, looking for u squared, and I'm looking for a squared. So u squared in this case is x squared. U is equal to x by taking the square root of both sides, and du is equal to 1. So I don't have to worry about any kind of compensation with a u substitution. A squared is 9, taking the square root of both sides. A is 3. So for inverse sign, I will have my 5 coefficient. Inverse sign, you can write it as arc sign or inverse sign. The AP uses the inverse sign with a -1 power. Make sure that you understand that that does not mean 1 over sine or cosecant. Sine with the -1 power means the inverse sine function. So just make sure that you are aware of that. All right, so back to what we were doing. We have u, which is x over a, plus c. Problem number 1. All right, let's clear the board and go back to problem number 3. In problem number 3, I don't see the square root, but I do see the plus and the square, so I'm thinking that we're headed toward arctangent. I'll bring my 7th coefficient out front, and I'm going to identify u squared, which in this case is x squared, and u, taking the square root, is x, and du, making sure I don't have to compensate, is 1. A squared is equal to 16, therefore a, taking the square root, is equal to 4. The inverse tangent formula tells me 1 over, or in this case the coefficient 7, over a, inverse tangent of u over a. U is x, a is 4, and don't forget the plus c. Never forget the plus c. Number 4. Number 4 looks similar. I'm going to do a little bit of rewrite. I am noticing a little bit of difference here in that I have a coefficient of 9. So I'm going to be careful with that. I'm going to bring the 4, just like I have in all the other problems, that coefficient out front. So I'm going to identify u squared, in this case to be 9x squared. U, by taking the square root, is 3x, and here's the important part, du, or it's all important, but this is an important part, is 3dx. So I'm going to compensate by dividing both sides by 3, and that 1/3 is going to go in front of my final answer. So make sure you remember the 1/3. A squared in this case is 1, therefore a is 1. And since we're looking at inverse tangent, we will have, so here's the 1/3 from the u substitution. Here is 1 over, we have the coefficient of 4, so we have 4 over a. I'm just emphasizing that. Inverse tangent of u, which is 3x, over 1, or over a, plus c, and so that's going to give me 4/3 inverse tangent of 3x plus c. Problem number 4. Don't forget the c. Number 6. In problem number 6, I don't see a square root, but I see squares. I'm thinking inverse tangent again. In this case, u squared, is equal to x minus 1 squared. U is equal to x minus 1, a squared is equal to 4, and a is equal to 2. I don't need to, oh, the derivative here is 1, so we're good to go on that. Don't need any compensations, so I will have 1 over a, so that's 1/2, because we're looking at inverse tangent. 1 over a, and then I'm going to do u over a, so I have x minus 1 over 2. Don't forget the c. Problem number 6. Moving on to problem 7. In problem number 7, now I'm slowing down just a bit. Now, I do notice if you compare number 7 to the first 5 that we've already, or 4 that we've already done, they had, in the numerator, they had constants. Now I have x cubed. Now, that doesn't mean that it's not an inverse trig, but the fact that the power is higher in the numerator makes me take pause. Because if I were to identify, so let's just say I was thinking arctangent. If I say u squared is equal to x squared, u is equal to x, du is equal to 1 dx. So that x cubed in the numerator is not going to help me out, and it's going to block me from having inverse tangent. So it looks like it wants to be inverse tangent, but it actually is not. So what strategy do we have when we have a larger power in the numerator than we do in the denominator? You got it, long division. So I'm going to do x squared. I'm going to put a placeholder for 0x, and then I'm dividing into x cubed. We'll see how far we need to go, plus 0x squared, plus 0x plus 0. Just putting in placeholders, sort of like place value with numbers. X squared times what makes x cubed? That's going to be x. So I multiply and I get x. 1 times x is x. And then I get 0x squared. X times x squared is x cubed. And that's positive. It doesn't matter. Subtract the whole thing. Subtract. That goes out. I have zeros here. 0 minus x is negative x. So that is my remainder in this case because x squared times, I'm not going to have a negative power. So that's my remainder. So I have the antiderivative of x. I'm going to put that by itself because I know what to do with that. That's just normal quote, in quotations. Then I have the minus. So here's the minus. Integral of remainder over divisor. So when I did that long division, it seems the second term is looking very much like an arctangent. So let's see what happens with that. With the first term, the antiderivative of x is x squared over 2. So that's easy. Now I'm going to come down here and I'm looking at the second term right here. And let's see if it's going to turn into arctangent or if I have to figure out some other strategy that's going to work here. So if I identify u squared, I would say that u squared is equal to x squared. I would say that u is equal to x and du is equal to 1. So that's not really working out either because the du is not equal to x. So if that's not going to be arctangent, as I suspected, what are my other strategies? Well, I can't use long division because the power in the numerator is greater than the power in the denominator. Well, what other strategies do we have? Let's think about u sub. So if we let u equal to the denominator of x squared, du, seems like we're getting somewhere now, is equal to 2x dx. I don't need that 1/2, so I'm going to divide it to the other side, and I have x dx. So I want to take a moment to pause, and hopefully you're realizing the strategies and the thoughts and how I had to get to how I was actually going to find the antiderivative of that second piece, or the second term of this antiderivative. I thought, well, maybe it's arctangent, and I took that path as far as it would go, and when it didn't go anywhere, I had to back up and go, well, let me go back in the toolbox and find another strategy. All right, so use substitution seems like it's going to be how we're going here, so I'm going to write my new problem down here. Again, I'm looking at the orange second term up here. So I will have a 1/2 out front. In place of x dx, I'm going to substitute the 1/2 du, and in place of x squared plus 1, I'm substituting u, and that's going to be du. So that's going to give me 1/2. The antiderivative of 1 over u is ln absolute value of u plus c. I'm going to bring that back up here and resubstitute, and remember there was a minus from here. So that's 1/2 ln absolute value of x squared plus 1 plus c. Don't forget the c. All right, let's go on to number 8. Let's reset this page so we have a clean slate to work from. In number 8, I see x squared plus 1 in the denominator. That makes me think about arctangent, but in the numerator I have a greater power. Could do long division, but I'm also noticing that I can factor the numerator as the difference of two squares. So let's see where that goes. Because remember, it's all about strategies. What can I do? It's about stopping, looking at the problem, thinking about what would be efficient, what might work. So if I factor x to the 4th minus 1, and here it comes, I get x squared plus 1, times x squared minus 1 over x squared plus 1. So using my basic algebra of factoring was a beautiful thing, because I can divide out the common factor in the numerator and denominator. And that leaves me with the antiderivative. Oh, I love this because it's just quote-unquote normal now that I've manipulated. That gives me x cubed over 3 minus x plus c. What a nice and easy problem. So don't make assumptions. Analyze the situation. Use all of your tools. Going on to problem 13. In problem number 13, I am noticing squares in the denominator with a plus. I could try use substitution. I think because these are perfect squares, I think I'm going to start with trying to see if this will go to inverse tangent. Notice I say I think I'm going to try that because I'm working these problems from scratch. I'm working them cold. So I have to think about my strategies. So if I think I'm going to head towards arctangent, I would say that u squared is equal to e to the 4x. And if I take the square root of both sides, u is equal to e to the 2x. And the derivative of e to the 2x by remember, the derivative of e to a power is e to the power times the derivative of the power. So that gives me 2e to the 2x, which is what I wanted in the numerator. So I'm going to divide the 1/2 to the other side, remembering that that's going to have to be compensated for in front of my answer as a coefficient. A squared is going to be 4, and a is going to be 2. So I do have the format of inverse tangent, so I have the 1/2 from down here as a coefficient, times 1 over a is 2, so I have another 1/2. So this 1/2 comes from here, this 1/2 comes from here. Inverse tangent of u, my u is e to the 2x over a, and my a is 2, plus c. Simplify, that's 1/4. Inverse tangent of e to the 2x over 2 plus c. So that takes care of the first set of problems. So let's go to the next page for me. And let's hit 21 and 23, and we're moving from indefinite integrals to definite integrals. So problem number 21 looks very much like inverse sine. So let's see, pretty sure that's going to work out for us. U squared is equal to 9x squared. U is equal to 3x. Well, no, it's not. Come on, Jernigan, you can do better than that. All All right, let's try that again. U is equal to 9x squared. Oh, yes, U is equal to 3x, and du is equal to 3dx. So we're going to divide the 3 to the other side, and we're going to need to have that compensation as a coefficient. All right, so a squared is equal to 1, a is equal to 1. So I have inverse sine, inverse sine of, I'm getting ready to sneeze, I'm going to pause. So u is 3x, a is 1, so I have 3x. Don't forget that 1/3 that we have in front. And we're not going to have a plus c in this case because we are dealing with a definite integral, and I'm going to keep the 1/3 out front out of the way. My bounds are from 0 to 1/6, so let's substitute. We're dealing with FTC part 1. So there's 1/3. I'm going to put in the upper bound, and 1/6 of 3 is 1/2. So sine inverse, again, I'm substituting the 1/6, and that's going to give me 1/2, 3/6. That is the upper bound substituted, minus the lower bound substituted, inverse sine of, and 3 times 0 is 0. So I have a 0. All right, now think about, go back to pre-cal. When I have inverse sine of 1/2, what I'm really asking myself is, what is the angle measurement with a sine of 1/2? Also, the other thing you have to remember about inverse trig is the quadrants that you are allowed to actually search for these angles. So for inverse sine, it is the rotated positively into the first quadrant and rotated negatively into the fourth quadrant. So since the 1/2 in this case is positive, I know that my angle is going to come out of the first quadrant. So think about it. What angle in the first quadrant has a sine, a y value of 1/2? And that's going to be pi/6 or 30 degrees. Now I'm going to ask myself the same thing. What angle in these two quadrants has a sine or a y value of 0, and that is 0? So then when I simplify, I get pi/18 as the accumulated net area under that curve. That was number 21. Going on to number 23. Looks very much like we're headed now into inverse tangent. So if that's the case, my u squared is equal to 4x squared. U is equal to 2x, taking the square root of both sides. Du is equal to 2dx, and I'm going to divide the 1/2 to the other side. And remember to put that coefficient in front. A squared is equal to 1, and a is 1. So for inverse tangent, remember we have 1 over a. So in this case, that would be 1/1. We're going to need our coefficient of 1/2. So I have 1/2 inverse tangent of u over a. So u over a is 1, evaluated from 0 to square root 3 over 2. No plus c because we're evaluating a definite integral. So I have 1/2 inverse tangent of 2 times root 3 over 2 is simply going to be root 3. Upper bound minus lower bound, inverse tangent of 0. So the same thing for tangent, I am also allowed to only look in the first quadrant rotated positively and the fourth quadrant rotated negatively. And since both of these values are positive, then we are going to be looking in the first quadrant. So what angle has a tangent of root 3? Now how you know that or how you figure that out varies from student to student, and how good they are at their right triangle trig or their unit circle trig. So remember that tangent is sine over cosine. So I'm trying to produce root 3. So the question would be, does that come from root 3 over 2 over a half, or does it come from 1/2 over root 3 over 2? So if I multiply this out, I would have root 3 over 2 times 2 over 1, which gives me root 3. So that tells me that I need for the sine to be root 3 over 2 and the cosine to be 1/2. So whichever trig function you want to think about, what angle has a cosine of 1/2? That would be a 60-degree angle, which is pi over 3. So I have 1/2, let's make that neater, 1/2, this evaluates to be pi over 3. The angle that has a tangent of 0, again, remember we have sine over cosine, so the only way we can output 0 is if sine, the numerator, is equal to 0, and we just said in the last problem that for sine to be equal to 0, we have, we have an angle of 0, and when I multiply, I get pi over 6. So I want you to understand 21 and 23 are not hard. You just have to use your trig, and it's really good practice for you to do that. 31. In problem number 31, I see trinomial denominator, 1 in the numerator. I have a feeling that we are back to completing the square. So but it's a definite integral, so over here on the side I'm going to complete the square. X squared minus 2x, kick out the constant, half of 2 is 1, so I'm going to add the 1 and subtract the 1. Remember the steps for completing the square. Kick out half the coefficient of x and then square it, add and subtract. Factor, that makes x minus 1 squared plus 1. So my new integral is now 0 to 2 of 1 over x minus 1 squared plus 1 dx. Hopefully you recognize this as inverse tangent, so u squared is equal to x minus 1 squared, u is equal to x minus 1, du is equal to 1 dx. So I don't have to have any compensations. A squared is equal to 1, a is equal to 1. So the inverse tangent is 1 over a, so that's 1 over 1. Inverse tangent of u over a, my u is x minus 1, and that's over 1. Evaluated in this case from 0 to 2. So inverse tangent of 2 minus 1 is 1. And inverse minus, upper bound minus lower bound, inverse tangent of substitute 0, I get negative 1. So let's go back to pre-cal. Remember I said for inverse tangent, you're only allowed to look for positive outputs in the first quadrant and negative outputs in the fourth quadrant. So here's my positive output. If tangent is equal to 1, then that means sine and cosine have to have the same output, which would be root 2 over 2, which would put me at a pi over 4 in the first quadrant. So the tangent, inverse tangent of 1 from the first quadrant is pi over 4 minus, now be careful, when you go into the fourth quadrant, we are rotating negatively. We're rotating in the opposite direction. So the angle in the fourth quadrant that has an output of negative 1 would be negative pi over 4. So pi over 4 plus pi over 4 is 2 pi over 4, which is equal to pi over 2. Oh, my pen, something's going on with my pen here, sorry. 32 is pretty much the same problem as 31, so I'll leave that to you, and you can use the solutions manual to check that. I do, however, want to do number 41. That might freak you out a little bit because it's x to the 4th power, but notice that it's x to the 4th, x squared. It fits the same pattern that the power in the first term is double the power in the second term. So really, it's the same situation we had before. It is completing the square because there's nothing else we could do. We could let u equal to the denominator, but the derivative of x to the 4th just by itself is 4x cubed. So that's not going to, the numerator of x is not going to take care of that as a derivative. So I'm going to go with complete the square. So I have x to the 4th plus 2x squared, and I'm going to kick out the constant. There's the plus 2. Half of the coefficient of, in this case, the middle term, half of the coefficient of x squared is 1. Squared is 1, so I'm going to add 1 on the inside, subtract 1 on the outside to make 0. I'm going to factor, and that'll give me x squared plus 1 squared plus 1. So let's see what happens. That gives me a new problem of square root of x over, well, not a new problem, but a rewrite. Think like it, I think it's headed to arctangent, so I'm going to say u is equal to, or u squared, I'm sorry, is equal to x squared plus 1 squared. U is equal to 2, whoops, nope, u is equal to x squared plus 1. There's lots of squares here. X squared plus 1, I didn't need to put that parentheses. Du is equal to 2, and here it comes, x dx. So there we have it. There's our x dx being compensated for. I don't need the coefficient of 2, so I'm going to divide it to the other side. I'm going to remember that it's got to go in front of my answer. And that's going to give me my x dx. The value of a squared is 1, and a is 1 also. So this is an indefinite integral, so I will need to remember plus c. Here's my 1/2 from here. And I'm going to have 1 over a, and a is 1, inverse tangent of u, here's my u, x squared plus 1, over a is 1, plus c. So it might have looked scary to begin with, but it really is not scary. It's just still completing the square. So there are your answers and your workouts for these pages.